Okay, so I have opened the MATLAB and Simulink on my computer here, and I'm using the Mac OS version of MATLAB release 2016B. If you're using a newer or older versions of MATLAB for PC, for example, you will probably see a slightly different in terms of the menu arrangements. So what I have done here, I have constructed the closed-loop speed control for the DC motor drive using Simulink blocks as shown here. This is the DC motor. If you double-click that, you can see that this is the transfer functions of the DC motor that we have developed before. This is 1 over SL plus RA, the torque constant, and then we have 1 over Sj plus B, and then we have the back EMF constant, so we have the back EMF here, VA minus the back EMF times that transfer function gives you current, and the current times the torque constant, you get the torque here, and torque is multiplied with 1 over J plus B, you will get the speed. This is the transfer functions of the converter, which is just a DC gain with the numerical values of 12, because our DC voltage, if you remember, is 60 volts and our peak value of the triangular wave is 5 volts. So 60 over 5 is 12. I will be using body plot to design the PI controllers for the torque and speed loops. As we have discussed earlier, we will start off with the innermost loop, which is the top loop, and design the PI controller for the torque. At the beginning, I will set the KP and KI of the torque controller here to 1 and 0 respectively, so that the PI controller is just a unity gain and will not contribute anything to the body plot. Okay, so we will now start the design. We go to the analysis menu, control design, and I will select the control system designer. Okay, so we have opened the control system designer window here, and the first thing that we need to do is to define the architecture of our systems. The first tab here, which is the blocks tab, is where we need to define which block in this Simulink we want to tune. Okay, in our case, obviously we want to tune the torque controller, which is the PID controller 1 here. So what I will do is I will add the blocks, which is the PID controller 1 here, and then click OK. And then you go to the signal tab here. Since we just added the PID controller 1 as a tune block, then the automatically the output of the PID controller will be added to the locations of the signal. We can add the locations of the signal here, or we can define it later on. Okay, since we are designing the torque controller for the torque loop, then we need to open the speed loop. So this is where you define the openings of the loop. You look at this Simulink block here. What we will do is we first open that speed loop. So I will define that as the opening, and I will only left with the speed loop here. So you add the openings and you click where you want to add the openings in the Simulink model. So I will click it here, go back to the block here, and as you can see that it is added now. Sum 1, which is the output of sum 1. You add a signal. Alright, so and for the linearization options, I will leave as it is because our model is already a linear model, so we don't need to define any points or DC points where we want the system to linearize. Okay, so you just click OK. Alright, now we have to define which method that we want to use to tune the PI controllers that we have selected. You go to the tuning methods tab here. There are several ways of tuning the PI controllers. What we will do is we'll choose the body plot, which is the top one here. So this is the body plot of the top open loop transfer function without the controller. That is when we set the controller to be a unity gain. As we have expected, the open loop transfer function for the DC motor contain 1, 0 and 2 poles. So we have 1, 0 and 2 poles. Locations of these poles and 0 are basically determined by the parameters of the DC motor, as we have seen earlier. If you want to look at the values of these poles and 0, you can obtain by plotting the pole 0 map of the system. If you go to the new plot here and you go down to the new pole 0 map, at the plot, then you will see that here you have one pole which is at -348 radian per second, another one which is at -36.4 radian per second, and a 0 which is at 0.0658. If you look at the transfer functions that we have developed before for the DC motor, permanent magnet DC motor, the transfer functions between the current or the torque and the voltage, which is what we just plotted just now, contains 1, 0 and 2 poles. Okay, the 0 is basically located, for example, here at B over J, and we have designed the system with B equals to 10, about 10 minus 6, J of 152, which means that our 0 is basically at 10 over 152, 0.0658, which is exactly the same as what we have here. Okay, I will close the pole 0 map now, and I will add the closed loop body plot of the top, so that we can identify the closed loop bandwidth easily. Okay, so you go to the new plot, add the new body. Now we choose the new input-output transfer function, transfer response, sorry, and you add the input signal. Go to the Simulink. This is going to be the input signal. Again, let me just add that again. Input signal. Add the signal. And then select signal from the model. So this is our output. Add the signal. Okay, and then compute input-output response with the following loops open. Since we have defined the openings before, then we don't have to add the opening of the loop here. So we just plot that. Okay, and then I will rearrange that. So this is the open loop plot, and this is the closed loop plot. Okay, when we change the Ki to a non-zero value, the PI controller will immediately contribute a 0, an integrator, and a DC gain to the body plot. And we can select the value of the 0 locations of the PI and the DC gain independently by changing the values of Kp and Ki. However, we have no control over the integrator. Okay, and then by selecting the suitable values of Kp and Ki, we can shape the open loop body plot so that the suitable closed loop bandwidth can be achieved. Right now, the bandwidth is, in fact, there's because the open plot never just 0 dB, so there is no crossover frequency here. Now, if I add a non-zero values to Ki, then as I said, there will be an integrator, there will be a DC gain, and there will be a 0, 1, 0. Okay, so let me just first add the an integrator, and then I have a choice of selecting a 0 locations, and I will do that. I will select a 0 location, a real 0 in between this pole. For example, if I put a 0, then I have a complete PI controller which is not tuned yet. Okay, which is not tuned yet. As you can see that the crossover frequency or the bandwidth is at around 0.0012. Okay, 0.0012, which is somewhere there, or you can see from here. Okay, you can see from there the crossover frequency. The switching frequency of our systems, which is the triangular, is at 20 kilohertz. So as I said earlier, then the top closed loop top bandwidth has to be a decade lower than that, which is 2000 hertz, and that is equivalent to 12.56 kilo radian, or 1.25 times 10 to the power of 4 radian per second. So let's move up the gain now, so that we can achieve that crossover frequency of 12.5, about roughly 12.5 kilo radian per second. So I will move up the gain now. As you can see, as I move up the gain, the crossover changes. Okay, that is not enough, so I'm looking for 12 point or 1.2 around. It's not going to be.
It's 3 o'clock.
Okay, that's about it. 1.23 times 10 to the power 4. So that is our okay. Let me change the range of frequency for the open loop plot to be the same as the closed loop plot. Okay, so we add another 0 here. Okay, now you can see the crossover frequency of the open loop plot, which approximates the closed loop bandwidth, where the gain of the closed loop plot is minus 3 dB. So let me add the 45 degrees grid here. Okay, and I will add the grid here as well. Okay, I can now see the value of the KP and KI with these settings, or with this body plot, by clicking right here and edit the compensator. So this is the values of the PID or PI controller that we have designed. So instead of using 63.02.2, I will round off the values to say 6300. And the locations of the pole, let me just round it off to minus 118. Okay, so that is the final value of our top controller, with a phase margin of 91.2 degree, which is way higher than our requirements of 65 degrees, and a gain margin of infinity. Okay, we can now update the values of the KP and KI in our Simulink by pressing that button there, update blocks, and if you go to the Simulink, you can see that the values of the KP and KI now is changed to the values that we have designed. Now we are ready to design the speed controller, which is the outer loop here, the speed controller. So I will go back to the controlSystemDesigner and start over again, repeat the same process as we have did before. We go to the architect, we just remove the responses first, delete it, and then we go to the architecture and remove everything here, as well as the openings, and we remove the PI top controller, and we add the new tune block, which is the PI speed controller. So we add the block and choose the PID controller here. You can highlight the selected block if you want, which is that one. Okay. And then we just leave as it is for the signals, as well as for the linearization options. And we click OK. Alright, now we will add the tuning methods. Again, we're going to use the body plot, the new loop transfer 1, and we select the response, which is the speed now. And there is no open loop, there is no opening here. Okay, so we plot it, and this is the body plot of the open loop speed transfer function. This is the pole due to the closed loop top bandwidth, and as we expected, there is only one pole, which is located at B over J, which is roughly at 0.066 radian per second. If we are to assume that the top loop band gain is unity, then there will be no pole located here, regardless of whether the top loop is assumed unity or not. It will not affect our closed loop speed bandwidth because it is located a decade lower than the closed loop top bandwidth, which is roughly here at 1.25 kiloradian per second. Okay, let's design the speed controller now, and what I will do is I will add an integrator, a pole, and I will adjust the gain accordingly so that we can get the bandwidth, which is the crossover frequency of the open plot, to be at roughly around 1.25 kiloradian per second. But before I do that, let me add the closed loop plot of the speed loop here, and we go to the new input output transfer function, add the input signal, which is going to be here, and we add the output signal, which is going to be the speed here. Right, and there will be no openings. So we plot the closed loop body diagram, and let me rearrange that. And remove the okay, so this is the open loop plot and this is the closed loop plot. Alright, as you can see that the crossover frequency of the open loop, which approximates the closed loop bandwidth, is around 5.8 kiloradian per second, which is higher than it should be, at around 1.25 kiloradian per second, right? And you can see that here, that is approximate by minus 3 dB gain on the closed loop plot.
It's 12:30.
Okay, so I will add the integrator first. and then I will add a 0 to which cancels out the system pole. It's roughly located somewhere here, so let me put it down first. Alright, so we add a 0, cancel that pole, and now we will adjust the gain so that we can get the crossover frequency of at about 1.25 kiloradian per second. Okay, so I will increase that. 1.25. Let me maximize the windows first, and alright, I think that is the closest I can get, which is at about 1.29 kiloradian per second. So the closed loop torque bandwidth is there, and our closed loop speed bandwidth is a decade lower than that, which is around that frequency. Okay, and the phase margin is 84.1 degree, which is higher than 65 degrees that we have set. Okay, we can now look at the values of the PI controller's parameters by, as before, clicking the edit compensator, so that these are the values here. Let me round off the numbers to, let's say that we have 0.135. Let me remove that 31, and the pole, say that's put as 0.0671. Okay, and you can now update the PI controller on the Simulink by clicking these update blocks here. So if you go to the Simulink, then you'll see that the values of KP and KI now is updated according to our design. Okay, we are now ready to verify our controllers with a large signal simulation. The verifications with a large signal model is important or required because the controllers that we have designed, the two controllers, PI controllers that we have designed, is based on the linear model of the system, which is a linearized model of a nonlinear system which contains switchings, power electronics, and saturation blocks, and so on. So in order to make sure that our controllers, which is designed using the linear model, really works with the actual nonlinear system, then we have to do the verifications. So let me switch now to the large signal simulation I have developed here. Okay, this is the large signal simulation model that I have developed using Simulink. This is the DC motor, which I have masked so that if you double click it, you can change the parameters, and these parameters are now set to the values which is the same as the small signal model that we have used before. You can look underneath the mask by clicking this small arrow there, which, as you can see here, is exactly the same as the model that we used for the small signal. The output voltage of the converter across the motor armature, which is VA here, is a combination of the output voltage for each leg. Okay, we have one leg, output voltage of one leg, and we have the output voltage of another leg. So we have a voltage across one leg minus a voltage across the other leg, gives you a voltage across the armature terminals. The difference between the two is the armature voltage or the output voltage of the converter. This model uses the unipolar switching scheme so that the control signal for each leg is different, meaning that the control signal of one leg is the inversion of the control signal from the other leg. Both control signals are compared with the triangular wave generator, which is here, which is also masked, so that if you double click that, you can change the frequency and the peak value of the triangular wave, which I have changed to 20 kilohertz and 5 volts for the peak triangular wave. This is the PI controller for the top loop. It is the input to that PI controller is of course the torque error, which comes from the motor torque and the reference torque here. So the torque reference, which is the input to this top loop, is clamped to the maximum and minimum values of 1.5, which is implemented using that saturation there. 1.5 Newton meter and the minus 1.5 Newton meter respectively, which is assumed to be the maximum allowable torque values. And it is coming from the PI controller for the speed loop. So this is the reference signal, which is set to have a profile which is shown here. Okay, so now what we will do is we will copy the PI controls that we have designed using the small signal model here, and then paste it here. And then I will replace this PI controller with exactly the one that we have just designed. If you click the top controller, then it gives you the values that we have designed. This is the speed controller, which is exactly the same values that we have designed earlier. Okay, let's start the simulation. So I will start the simulation. Okay, I'm displaying two channels to the scope here, the speed and the torque. For the speed channel, you have two signals coming from the reference and from the motor speed, and for the torque, you have the motor torque shown here. So let's double click that. This is the speed and this is the torque. So as you can see that the actual motor speed managed to follow the reference speed during the acceleration from 0 to 150, as well as during the speed reversal from 150 radian per second to minus 150 radian per second. And then we have a step change in the speed from minus 150 to plus 150 radian per second, and the speed of the motor accelerate with a linear acceleration, which is limited by the 1.5 Newton meter that we have set in the saturation block, as well as during the deceleration from 150 to 0 radian per second. The deceleration is a linear deceleration with a maximum torque limited to minus 1.5 Newton meter. And if you zoom to the torque signal here, you will see that this torque actually contains ripple, which is as what we expect due to the switching of the 4-quadrant DC-DC converters. So you have a ripple in the current as well as in the torque. That is all that I want to present in this tutorial, and thank you for watching, and see you next time.